So hello together. Today we want to use our knowledge of a transmitter-receiver system to discuss a deep space communication link. In our exercise 3 problem 5 it's written to communicate with the Earth. A Mars orbiter uses a frequency of 8.5 GHz. On Earth we have a parabolic antenna with a diameter of 70 meters and the transmitting antenna on the Mars orbiter has a diameter of 3 meters. The average distance between Earth and Mars is 2×10⁸ kilometers. And here we have got an equation to calculate the gain of our antennas. But in the next step, we want to use our transmitter-receiver system in free space. And we know this transmitter-receiver system is described by this equation. And now I want to divide both sides by milliwatt. And we will take 10 logarithm of both sides. So we will end up in this equation here. We have 10 times log PR with respect to 1 milliwatt, and this is the definition of PR in dBm. And here we have 10 log GR, and this is the definition of GR in dB. So this is a definition of GT in dB. And a little bit different is this term here. It's 20 log times the denominator. And because of its denominator, we have here a negative sign. And because of the square, we have here 20. And in the last equation, we have 10 times log P with reference to 1 milliwatt. And this is nothing else but the definition of PT in dBm. And the whole thing is called the link budget of a communication link. Instead of using this formula now in the dB scale, everything is reduced to addition of dBs or dBms. And in the next step we will now calculate GR and GT in dB. So at 8.5 GHz we have a wavelength of 3.53 10⁻⁻2 meter. And if we use our equations, then we end up in a linear scale of GT. The gain of the transmitting antenna would be 7.128 10⁻10, which corresponds to 48.5 dB. Using the same equation, we can calculate the gain of the receiving antenna, but of course here we have a 70 meter diameter. This is a quite large scale. In the gain in the linear scale, we have 3.88 10⁻7, which corresponds to a dB value of 75.9 dB. And now we come to the third term in our link budget, which is called the so-called path loss. It describes the damping due to wave propagation in free space. In our case, we get that L divided by dV is proportional to this value. And here you have to be careful because the distance was given in kilometer. You have to change the kilometer into meter, and we end up in a value of 277, which says that the distance between Earth and Mars results in a signal damping of 277 dB. And now the question arises, calculate the received power at the Earth station in dBm if the orbiter transmits a power of 100 watt. So in the first step we must change the transmitted power from the linear scale of 100 watt to the dBm scale, we have P divided by dBm is 10 times log 10 to the power of 2, which means 100 watt. And here we have 1 milliwatt, so the watt will cancel and we end up in a value of 50. So now we can apply our link budget. So the received power in dBm is given as the sum of these numbers, and so we result for the received power on the receiver side in a value of PR is minus 102.6 dBm. And now the question is, which bandwidth can be used by the communication system if it is operated at room temperature and an SNR is of 20 dB is needed. So first I must change the SNR value, which is given at this equation, to the dB scale, and in the dB scale the division of the two terms ends up in the subtraction of the two terms. And if we apply the numbers, we can say the noise level in dBm must be equal to minus 122.6. So if we consider communication links, the most important noise contributions come from terminal noise. And according to Poissar, we can calculate the maximum available terminal noise power by this equation. Here we have N is equal to the Boltzmann constant times the absolute temperature times the bandwidth of the bandwidth of the system. So you see, the higher the bandwidth of the system, the higher the noise level. So for room temperature, we assume that we have T equal to 290 Kelvin, and we can of course also change this equation into the dB scale, and then we end up in N is equal to minus 174 plus 10 times log the bandwidth with reference to a hertz, and this is the value in dB, in dBm. And if you calculate this value, then you end up in a system bandwidth of 140 kilohertz, which corresponds to a data rate of approximately 280 kilobits per second. So, but since the important contribution comes to terminal noise, we can also downcool our receiver. So to which value the bandwidth of the communication system can be enhanced if the receiver is operated at a temperature of 10 Kelvin. So now the absolute temperature is 10 Kelvin, which will reduce this value. The former value was minus 174. Now we have here minus 188.6. And of course, if you increase the bandwidth, this value will increase. So to reach the possible terminal noise level of 128 dBm, we can now use a higher bandwidth. If you insert the numbers, you will end up in a bandwidth of approximately 4 megahertz, which corresponds to a data rate of round about 8 megabit per second. So you see, even so we used a quite simple model, the results correspond quite good to published data. So thank you for watching the video again, and your comments are welcome. Please join again.